Officials and the community at large to honor Dr. Charles Towns, our longtime supporter and advisor of the Institute. We are also deeply honored to have with us Nobel laureates Dr. Arno Penzias and Douglas Osheroff.
And I welcome all of you, and we are very proud and honored to celebrate the birthday of our leader, our advisor, Nobel laureate Charles H. Towns.
Thank you, Dr. Gosh. Our next speaker was awarded the Nobel Prize in Physics in 1996 for his work and discovery of superfluidity in helium. He currently serves on the Board of Advisors of Scientists and Engineers of America, an organization focused on promoting sound science in American government. He is a professor of physics and applied physics at Stanford University. Please welcome Dr. Douglas Osheroff.
And we can all hope that we will be as productive at age, well, me personally can hope that I'll be as productive at age 80 as Charlie is at 95. But I don't think it's going to happen. And so this is actually, I like this picture of you, Charlie. I don't know about whether you like it or not, but it's one of my favorite pictures. Shedding light on scientific progress. And so this is a picture, again, one of my pictures of the Grand Canyon at sunset, and what I say is that those discoveries that most change the way we think about nature cannot be anticipated. How then are such discoveries made, and are there research strategies that can increase one's chances of making a discovery? Now you notice I say discoveries specifically rather than advances, because discoveries are usually things that frequently are not anticipated, and one doesn't know what's going to come out, whereas an invention or something like that is a very different sort of thing. Advances in science are seldom made by individuals alone. They result from the progress of the scientific community, asking questions, developing new technologies to answer those questions, and sharing their results and their ideas with others. To have rapid progress, one must support scientific research broadly and encourage scientists to interact with one another and to spend a bit of their time satisfying their own curiosities. This is how advances in science are made. Thank you.
Robert is also an active environmental leader who founded and heads the World Rainforest Fund, a non-profit foundation dedicated to saving Earth's tropical rainforests. Please welcome David Seaborn.
I have been given the impossible or semi-impossible assignment. Obviously it's not impossible because I accepted it, to talk about three giants of science. Those are Linus Pauling, my own father Glenn Seaborg, and the honoree of today, Charles Towns.
He was a former student of Dr. Towns, and his work in radio astronomy, especially his part in the discovery of cosmic microwave background, which provided evidence supporting the Big Bang theory of the origin of the universe, earned him a Nobel laureate in physics in 1978. He is currently a venture partner at New Enterprise Associates. Please welcome warmly Dr. Penzias.
It's both a pleasure and an honor to be here today to talk about Charles Towns. When I was a young graduate student, right out of the Army, my first course, the first series courses, one was optics. I took it just because I didn't know what to take. I'd been away from school for 2 years to be in the Army. I took a course in optics. I got in this course, and Charles Towns was the teacher. And it was unlike, the course was fine. And then we sat, a large number of us in a large auditorium. And I can still remember sitting there. And we got the open book exam. And it just didn't look like optics to me. Very puzzled. It was about an airplane flying over a mountain, and the waves moved down into and moved into an observer, and all these effects became real and physical. And none of us knew what to do, because these were not spinning back stuff from the text. These things we had to think about. And I got very scared. There were 5 questions. And of the 5, I sat there, couldn't do the first 4. I figured, well, I can't be the stupidest person in the room if I am. What are the odds of that? And so I did number 5 and went back and did some more. That was, the teacher there was Charles Towns. Because he thought by teaching this course in optics, he'd learn a little bit more about optics. Because he was thinking of microwave optics and the laser and light. And it was part of a transition for him, and he became a teacher by teaching that. And it was an unforgettable experience for me. I got a 54, it was the second highest mark in that class. But we were all thinking, everybody in the room was thinking. And I think of all the things I remember about Charles Towns, insights, was that ability as a teacher to train us to look at things in other ways. Charles Towns was born in 1915 in Greenville, South Carolina. His father was an attorney, but the family lived on a farm. And as a young man, he remembers doing chores and getting paid for them, working with his hands, learning about real things. Went on to college, went to Furman, where he graduated summa cum laude in modern languages and physics, even though Furman really wasn't the school that taught physics very much. They had a couple of courses in it. So the young Charles Towns just looked at some textbooks, read them, and did the problems. From there, he went to Duke University. He had an assistantship there to pay for his tuition and help him get along. But after a year, it was time to get a PhD. Got his master's degree, went to get a PhD. And there was only one assistantship. One assistantship. And he didn't get it. So here again was adversity, something he had to deal with. And he had $500 saved. And he went to California. He went to Caltech, where he got a PhD. He went and worked, and he did work with a Professor Smythe, author of a book called Static and Dynamic Electricity. I'm going to pick up my watch to make sure I don't keep you too long. And a very, very tough book. We as students were in awe of that book. We read it, we learned a little bit about it, but somebody once said, Professor Towns can do all the problems in Smythe. And we were just shocked. Well, it turned out a Smythe student, Professor Towns, not only looked at the student, he wasn't a professor in those days, he now looked at the problems, but corrected some of them to fix them up for his professor. And then he got a degree at Caltech and decided he wanted to do teaching and research. And he had a job at Bell Labs as well. He had a job. He didn't have another job. And the professors, as he tells it, said, take the job. And he figured, okay, he'll go to this, this lab, whatever it is. And guess what? He was able to do some research until about 15 months later. 15 months later, his boss came in on a Friday and said, Monday, you're working on radar. World War II was starting, and all of a sudden, his life was changed by this life, just because he was asked to do this and he had to do it. And the adversity led him on to starting to work on radar, microwaves. You may have heard something about microwaves. Something not many people knew about in those days. He was interested in spectroscopy, but didn't know about microwaves. This was not a field that actually existed. if you remember, he's now the author. He's the author of a book called Microwave Spectroscopy. There wasn't such a thing in those days, but there was radar. And at Bell Labs, and in this radar business, he also learned about electronics. But for the first time in his life, he had to do some teaching. Guess where the teaching took place? In the cockpit of a DC-3. He was in the back with his colleague, and they were testing a radar. And they swept this radar all the way around, and they could see the ocean, because this was supposed to be an airborne radar to be able to detect ships and such. And this airborne radar swept the sky, and they got their data, and we called up the cabin and said, okay, well, time to go home. But they had to turn their radar off. And they looked at the radar, and guess what? They were heading east, and they were in the Atlantic Ocean. If you're in the Atlantic Ocean, Florida is not to the east of where you are. And so young Charles Towns, Dr. Towns, got the pilot and taught him enough about radar to save the plane, all their lives, and his career. So he's working on radar. The radar in those days was at 3 centimeters, something those of us who deal with microwave call X-band. So just, these are the size. There are various sizes of this pipe that you use, and the one I used to work on cosmic background is about this big, X-band is about this big, and then there's even a smaller one called K-band, about so big, a little one. And they decided, the military decided they're going to start working on a K-band radar, a higher frequency. Well, Charles Towns knew it wouldn't work because there's too much water vapor in the air at that frequency. But they built it anyway. They didn't listen to him. And so they made him do it. But when he left, the war effort was over, he was back at Bell Labs, he now had K-band microwave equipment, which is a spectacular way of starting a new form of spectroscopy, a new way of studying molecules. And there he was. And so he went back to Bell Labs and he said, I'm going to work on microwave spectroscopy. And they said, fine, that's very nice, go ahead. Research was a good thing. Later on, he wrote a book with Art Shallow called Microwave Spectroscopy. But he's also interested in radio astronomy. Carl Jansky didn't stop the work because somebody at Bell Labs didn't want him to do it. It's not true. Carl Jansky could have used that antenna. In fact, it was used later for other things. I even met the man, I knew the man who had built Jansky's antenna. Didn't know Jansky himself. But Jansky did what anybody would do. This is what any competent scientist could do is, well, you think you have an astronomical result, after all, it has a sidereal variation, and it's and here we have a picture of him pointing at the center of the Milky Way. This is the Milky Way, we can see it in radio waves. And he actually went to the Palomar Observatory. Is this good for any? Well, what should we do with this? And he said, there's nothing in radio we as astronomers will ever need. Go away. And so Jansky did, at that point, start doing some other stuff. And then the war started anyway, and Jansky went on to other things. And in fact, his antenna, which you saw a picture of, I found a folder in one of the filing cabinets at Crawford Hill, where there's some of Jansky's old stuff, and I saw the latest embodiment of Jansky's antenna. The ears were cut off it, and they used it as a turntable to turn a microwave horn. So all that stuff was going on. But ultimately, in 1945, when Charlie wanted to do astronomy, it was something like 1945. He asked somebody, should we work this? And the answer was, no, it's not interesting. This was done in 1945 and 1946. Charles doesn't remember when it was. But 1945, 1946, optical astronomers said there's nothing in radio that microwave that would ever care about something. And 4 years later, Jan Oort in Holland, using the Würzburg antenna from a German radar, discovered 21 centimeter radiation, the hydrogen line, discovered hydrogen in the galaxy, and discovered the Milky Way. The motions, because you can't see it, there's just dust out there. But radio waves penetrate. So Jan Oort started the whole field, the astronomical field of radio astronomy, and so much that even the most bigoted optical astronomers couldn't stop it. Well, in 1947, he was doing microwave spectroscopy at Bell Labs, but couldn't decided to go to university, Columbia. He started with using this 1 centimeter radiation, the K-band microwave equipment that I talked about. And there, using that, the shorter the wavelength, the stronger the interaction. He got up a little bit early one morning and went down to Franklin Park and sat on a bench and said, well, you know, we have to somehow, we made this vacuum tube, that's great, but you can't, you want to go to shorter and shorter wavelengths, and you can't use shorter and shorter wavelengths. You can't make this stuff. What else could you do? We can't get them from molecules because the second law of thermodynamics says that things have to stay in equilibrium. And he thought for a minute. He said, wait a minute. And somehow, as he told me the story, sitting on the bench, and all of a sudden he realized, wait a minute. If you have a resonance structure, the whole idea of the second law of thermodynamics is random, but making or putting the molecules in a resonance structure, you can violate the second law of thermodynamics. You can get an equilibrium which actually can get you amplified. You can actually get you get coherent energy out. The maser was invented on that park bench because he understood that there was a loophole there in the law of physics. And then he wanted to work with this. He wanted to use this and do work on this maser at Columbia Radiation Lab. Now, I was a student there at the time, and there were some really famous professors there. There's I. Rabi and Polycarp Kush, both Nobel Prize winners on their own. And so Kush and Rabi went to speak to this young squirt and tried to advise him on his career. Hey, don't waste your time on this. Go back to spectroscopy. Do what you're doing already. But he needed 3 things to do that. One was his Bell Labs experience, because he knew about electronics. Actually, 4 things. He needed the Bell Labs experience. He needed a graduate student and a postdoc. And one more thing, tenure. Because he was tenured, he could tell these more senior and allegedly wiser professors, I'm going to do it anyway. And then, the next question is, if the interaction gets better, the shorter you make the wavelengths, how can you go to shorter wavelengths? And again, Charles Towns looked at the equations, and he said, well, think about that. And he thought using shorter wavelengths might be just as easy. By that time, he was a consultant back at Bell Labs. And so, what happened was, 2 mirrors in perfect phase. 2 mirrors in perfect phase. To get the resonator that would work at visible light. The idea of the laser was born as an invention. A patent was applied for. Over time, he gave of himself for other things. And he went to work at the Institute for Defense Analysis for 2 years. Well, in fact, while I was doing my thesis down in Maryland, doing my radio astronomy thesis, he went around and went there and started working on this stuff, and then from there went to MIT, because when he went from the Institute for Defense Analysis, he had a job at MIT. They said, please come and be our provost. We're looking for a president in 5 years. And 5 years, or some few years later, a very lucky thing happened. He had some students there, but a very lucky thing happened was they picked some non-scientist. And so Charles Towns once again, had the opportunity of doing something else. And he went to Berkeley. And here at Berkeley, as was mentioned earlier, he started the first search, the radioastronomical search for complex molecules, and found ammonia and water. And there were, this is a man who does looking for complex molecules. It was ultimately all based on his roots in a World War II assignment. Learning from experience, learning from whatever happens, so he could do something with it. And just turning things which other people might neglect and using them again. So he started with the complex molecules. Well, it turns out that others took up at shorter wavelengths. It required different kinds of antennas, and I did some of that with shorter wavelength and a shorter wavelength radio telescope, looking for more and more molecules. And the molecules of space turn out to be extraordinarily complex. If you look at the sky, you see this beautiful Milky Way, and it's interrupted with these total black messes which look like there are no stars there. But all they are nearby gas clouds, opaque to ultraviolet. Because the ultraviolet bounces off the outsides. The insides of these are made of crystals, very tiny flat crystals, graphite and ice, just flat, with cold and two-dimensional surfaces. So when atoms hit those surfaces, they can stay there. And more of them, they build up a bestiary of molecules, some of which we can't even reproduce on Earth. But there were enough of those molecules, all started from his work, enough of those molecules up there, all complex enough, that when that cloud, when some of those clouds were shocked by a nova, to compress, they're compressed tight enough as a ball of ice, or a ball of ice, which could actually get into the protosolar nebula and into the bottom of our ocean. And from there, the molecules of life existed. But time goes on, and one after another, opportunity of another, overlooked opportunities continue to the present day. All of the work, the expansion of the universe, Hubble's law, all that stuff, all the great things at Palomar weren't done at Palomar. They were done at Mount Wilson, which is a superb mountain site over a bunch of light pollution down there with Caltech and all that stuff, and all the smog and all the other things. Light pollution. There's light coming up from all of northern Los Angeles and the suburbs. So you can't use it anymore for optical astronomy. But it's still a superb view of the sky at the infrared. So again, with a bunch of students, built a couple of railroad tracks and made very precise infrared dishes. And from those interferometers, learned all sorts of things that nobody ever knew before. Betelgeuse. That's the star, the bright star, the third brightest star in the sky, Alpha Orionis, which is depends on how you look at it. It's Orion's left shoulder if he's looking away from you. It's on the left side. The left side, and that star was blowing off an enormous amount of its mass, which can only be seen from an infrared interferometer. And that is how the actual action, the life and death and evolution of these large stars, these massive stars in the galaxy, was first known to astronomy. As well as a whole bunch of other things I'm not going to go into, but cleaning up stuff which had been wrong and around for the better part of a century. People had done in optics, but when looked at with high resolution. And of course, that great discovery of all, measuring the mass of the black hole of the Milky Way. In all these years, Charles Towns has gone along. Last year, I found out recently, he has taken on his last students, decided not to take more students. And so we tried to figure out how many students he had. And the estimate is somewhere, not sure, it's somewhere around 7 dozen. It's one of these mysteries we can't really find out because the numbers don't seem to add up. One of the other things that was mentioned earlier again, all during this time, he wasn't just doing this stuff, but he also helped with other things. He was the chairman of the Scientific Advisory Board to the Apollo program until shortly after the landing on the moon. And during his time, that project was ahead of schedule and under budget. All I can really say about this man is, I think, the brilliance, the integrity, the genius, if I may. Underneath it is this extraordinary human being who's going to be the next speaker. Thank you.
Thank you. I'm so pleased and so much honored by this occasion and by the speakers. I would say, well, some of the people here and the speakers, such as Osheroff and Penzias, they deserve this kind of honor too, because they haven't quite reached 95 yet. So maybe in a few years we can also honor them.
Will you be there?
They deserve it.
Will you come?
Yes, of course. Assuming I'm around. Now, I also appreciate very much Dr. Gosh and his organization of this affair, and the many good things that he has done. And I want to say a few things about Dr. Gosh and his important work, and help out his nonprofit organization, the International Institute of the Bengal and Himalayan Basins. Dr. Gosh is a man of faith and integrity who has devoted his life to improving the lives in the developing world, and also helping populations in California and the rest of the United States, for that matter. He has been involved with the reduction of toxicity in ground and surface waters, as well as the discovery of new ways to implement and improve technology used in such processes. 3 Nobel laureates, including Linus Pauling, Glenn Seaborg, and myself, have supported Dr. Gosh's efforts, of course. I became aware of his work with Dr. Seaborg during the 1990s. And after Dr. Seaborg's death, I attended meetings of the nonprofit he co-founded, eventually taking an active role in the organization as an advisor. Dr. Gosh has dedicated 3 decades of service to improving drinking water in the Bengal Basin, as well as to environmental and minority rights. Additionally, Dr. Gosh has known the current president, dedicated secularist, Dr. Ziaur Rahman, for over 4 decades. Dr. Gosh has remained a close friend and associate of Dr. Rahman, and along with his commitment, proving through decades of work in the field and conference organization, his close relationship with politicians in India and Nepal, as well as Bangladesh, making him uniquely capable of expanding his mission in the Bengal Basin. Now, we humans are remarkable. We're a remarkable species. All the ways humans are changing life and changing this planet Well, that's great, but in these developments, we also endanger other species, as well as injure ourselves and change the planet. And so we have a responsibility. As we learn more and more and can do more and more, we have a responsibility for maintaining this as a livable planet, helping other species, and helping each other, especially those who are disadvantaged. So we must not just enjoy our success and sort of get as much as we can for ourselves. We must think of our responsibility, our growing responsibility, to look after this planet. Now, Dr. Geis has worked on these things, and after some years of working with him, I began to consider his organization for a chair in my name, and the chair was established in 2008, and for him. The purpose of this chair is a global operator using the Bengal Basin as working model to address the water crisis in emerging economies. The Himalayan and Bengal basins and their vast catchment areas are home to one of our planet's most important freshwater resources. The region includes vastly different hydrologies, geologies, and ecosystems, spans elevations ranging from the world's highest peaks to one of the lowlands on the planet. The differences in elevation, geography, and ecology make this region exceptionally valuable for developing remediation technologies for the rest of our planet. Now, to address these issues using his own resources as well as contributions from friends and volunteers, Geis's Institute has in the past arranged a number of international conferences concerning the impact of toxins on water resources and environment, measures to reduce the impact of global warming and sea level rise on the world's most vulnerable populations, sustain secularism and religious tolerance, and preserving the rights of women and the disabled, as well as religious and ethnic minorities. With these conferences, as well as 25 years in the field, developing models for the mitigation of water pollution, protecting water resources, and developing watershed management, Dr. Geis has earned the trust of the United States, Britain, India, Nepal, Bangladesh, and others. The goodwill that he has established with these governments makes him and his organization uniquely capable of expanding their mission and programs. I recommend the following things for the institution, and that we help it. Continue working on ways to combine Western technology and expertise with the expertise of the many professional people and scientists of the Indian subcontinent. This will involve commitment in the field, but also a program of education so the work can be expanded and be effective over increasing areas. Number 2, develop meaningful training programs for local leaders, professionals, and development managers that will help local communities improve their awareness and understanding of water issues and develop toxic mitigation strategies or solutions to these problems. Number 3, make use of information technology in educating people on water issues, toxic mitigation, and other environmental issues. Number 4, existing data already gathered in the Bengal Basin needs to be put together, analyzed, and published to be available not only to scientists and experts, but also to local communities in forms that are meaningful to them. Number 5, develop prototypes or working models of toxic mitigation measures that local communities will be able to adapt to their own environment. Number 6, continue advising public and private groups on technologies that provide solutions to arsenic and other toxic water issues. I'm sure you can think of the others. And we need to support Dr. Geis's wonderful work and that of his organization. With so much work in front of it, that organization will need the support of like-minded individuals who can share their time, expertise, or resources so it can fully and effectively carry out these official important missions and programs. Again, let us thank Dr. Geis and wish the best for his work and do our best to be helpful.
Thank you, Professor Towns. Our next speaker is the founder of IIBHD, and he's going to talk about some of the programs and the ideas that he has in mind in addressing the issues of the problems in Bengal. So let us all welcome Dr. Ghosh.
I
don't know no language to express my gratitude to all of you, particularly to Professor Towns, Mrs. Towns, and Dr. Penzias is my good friend, and Douglas Ashraf. I think I wanted to explain that Bengal Basin is a working model for emerging economies, and how more I learn about it, more I understand, how less I know about it. And then I thought that the groundwater contamination or toxic problem is seriously affected the Bengal Basin alone, but that is not the case. This has a kind of chronic problem all around the world. Land subsidence is knocking at the door in most industrialized cities or urban cities and industrialized regions. So I think instead of giving a picture or the story of Bengal Basin, which is very severe, for example, Kolkata groundwater, 90% groundwater exhausted, Dhaka groundwater, 70% groundwater exhausted. Due to tsunami or climatic adversity in ancient time, the thick aquitard in Buriganga was ruptured. So the filthy, polluted groundwater seeping into the crack of the thick, 300 feet thick aquitard are feeding the production aquifer, which is also very polluted. So Dhaka groundwater situation is slightly better than Calcutta, and Silicon Valley has a 600 leaks, and my colleague Dr. Dey, we talked earlier, we work on the same site on NASA as a kind of federal facility superfund site, and he inherited the site from me, which has an inter-aquifer connection when due to the rupture of the cylinder, the 36 cylinders, the thick aquitard broken down to an extent the groundwater pour into the San Francisco Bay.
Next speaker is longtime friend and associate of Dr. Gosh, as well as one of the founding members of the Institute. A chemical and environmental engineer by profession, his extensive experience in managing large and small environmental projects is here to talk about the work of Dr. Towns for the Bengal Basin. Let's welcome Dr. Derek Whitworth.
Briefly, the reason I'm here today is that about 15 years ago, Dr. Ghosh and myself worked together, and we got into many conversations about what Dr. Ghosh from Bangladesh, what we could do to try and help some of the problems there, particularly the issue of arsenic contamination in the groundwater. And I have to say that our ideas then on the theme of water were just like a little spring coming out of the rock, and hopefully we'd like to see the whole thing develop into a river, probably still at the spring stage.
Our next speaker is a longtime volunteer of the Institute. He is originally from Bengal, but has made Northern California his home for the last 20 years. A structural engineer by profession, he is currently working on a project in Bangladesh for the Institute. Generous contributor to IIBHB, speaking about the waters of Bengal Basin. Let us all welcome Dr. Shukamal Modak.
But currently, I'll talk about only on the one project which I did, a low-cost, efficient septic system design to alleviate the effect of groundwater contamination from untreated sewage or poorly designed sewage system. The motivation is to reduce the groundwater contamination, reduce health hazard, reduce the installation cost so that poor people can access these things, and simplify the design so that rural mason with little training can install these things. So it will be very simple. So what has been done, a simple design of septic system consisting of a set of septic tanks and a seepage field has been conceptualized. A pilot project of 6-tank septic system has been undertaken 6 years ago. then 4-year performance of the septic tank has been found to be very effective. We'll do more tests later. And the design incorporates low cost, local material, and simplicity in construction methods.
According to our president, Dr. Sterling Bonnell is a Renaissance man, and he needs a couple of minutes to explain what a Renaissance man is. And he is popularly known as a walking encyclopedia.
Thank you, Raj. I think we've had the good fortune today to hear 3 very remarkable scientists, open-minded, innovative, and open to exploration. I think it was Darwin's bulldog, Thomas H. Huxley, who said, "All human knowledge floats on mystery, and it is the task of science to push back the mystery as far as possible." Unfortunately, I think many scientists approach things with a closed mind, and so they're not in the exploratory mode. But we can feel very grateful for those who are. It appears that human scientific knowledge frequently advances more by improvements in instrumentation of observation than it does by logical debate. The invention of the telescope and the microscope made it possible for Galileo and Leeuwenhoek to expand our horizons. And these remarkable scientists who have spoken to us today have extended our horizons immensely. And interestingly enough, their work lines up in some very exciting direction. Charles Towns's work with lasers has made it possible to explore the possibilities of Bose-Einstein condensations through atomic lasers. And a Bose-Einstein condensation is a strange arrangement of quantum particles which unite under certain unique conditions and manifest at the macro level, such as superfluidity. It's called Bose-Einstein after Satyendra Nath Bose, who was a Bangladeshi scientist who was studying photons and statistically and came up with the original idea that they could condense. And Albert Einstein saw this and worked with him and published a paper in 1925. And since then we've found many increasing number of examples of this remarkable phenomenon, usually very close, taking place very close to absolute zero. Dr. Penzias's discovery of the infrared background radiation tipped the argument between Big Bang origin of the universe and the steady state universe in the direction of the Big Bang, and has led to a great deal of theoretical advancement since then. Dr. Osherov demonstrated superfluidity at close to absolute zero with helium-3. Charles Towns has also written on the possibility of a future convergence of science and religion and received the Templeton Award from religious groups for this. And one might hope that in the future that we could have some of the positive values of religion without denying scientific reality. And also that science could get a little humility about what we don't know. Since there are many things that we don't know. And one of the, as a psychiatrist practicing for 50 years, it seems to me that one of the reasons that scientific discoveries haven't produced the cultural transformation that we hoped for is that most people find it very hard to feel at home in a materialistic, reductionistic model of reality. And in the 20th century, the discoveries of quantum mechanics have changed that picture, but still, that's the picture that most people see. And I think there's a lot to be gained from explorations in this area. We don't understand consciousness. We don't understand qualia, which is why different modes of subjective experience are different. But some people think that the quantum realm may offer some answers to this. You may have heard of Roger Penrose, who has some theories about consciousness being related to microtubules, which he says can protect quantum phenomena so that they can occur on the macro level, and perhaps at something perhaps akin to superfluidity could occur at higher temperatures. I think there's a good deal to be said for this. And taking a little philosophical leap, you may have heard of the anthropic principle, that we look out into the universe and it looks like it's made for life. Why is this? There are two interpretations of this, the weak interpretation and the strong interpretation. The weak interpretation says, of course, it looks like it's made for us because we're here to see it. So this postulates an almost infinite number of dud universes, which we'll never see. This seems a little messy somehow, but the strong interpretation says that somehow life, and even conscious life, is intrinsically a part of the whole picture of the universe. One of the advocates of this is John Wheeler, the physicist and cosmologist, who says that only those universes that make observers get made. Now, I think that there's a practical difference to these two approaches. If we think the universe is just an accident, then the fact that we're here now is just the most extremely unlikely succession of accidents. And it's almost overwhelmingly unlikely that we'll survive the next crisis. It's sort of like you were going down a river in a canoe in rapids. If you thought the rapids would never end, you would get panicked and probably tip upside down. But if you thought that perhaps there was smoother water farther down the line, if you overcame the present situation, you'd have a better outlook. So if indeed consciousness and intelligent beings are intrinsic to the very nature of the universe, then perhaps there's room for improvement. And if we play our cards right, we might get there. Well, I'd like to make a final statement that Bangladesh is in a way very typical of many parts of the tropical world, which are heading for a crisis in the next few decades. And that the solutions which can be worked out there may have wide application.
Maybe we invite Professor Towns to come on stage for the presentation of the plaque of appreciation. It's a very simple plaque of appreciation, but it comes from our heart, from all the volunteers of IHB, and it reads, this plaque of appreciation is presented to Charles Hart Towns in gratitude and appreciation for his unwavering support of the Institute, its leadership, and its volunteers, for sharing his invaluable advice and guidance with the Institute in its search for solutions which address the necessities, provision, conservation, and equitable distribution of safe drinking water to the populations of the Bengal and Himalayan basins and the world, as well as the human rights of all people it serves. Given on this 24th day of July, 2010 in Berkeley, California. Signed, Rashbi Ghosh, founder, Sterling Bonnell, president.
I want to promise to this audience and the people of the rest of the world, the rest of my life I will work also to learn, establish, preach, and work to establish mutual respect, the mantra, the chant that I learned from my guru, Nobel Laureate Charles H. Towns, who were working with him 11 years. And Professor Towns is going to now live in a retirement home. He does not. He is one of the distinguished and simple men and being has all these opportunity, but he is going to live life like Ramakrishna. I'm so proud. Thank you.